Good morning everyone. So, we are discussing about the dialysis process during in the membrane based separation processes, and we have seen how to what is the driving force in a typical dialysis process, and what is the batch dialysis and what is the continuous dialysis. Now, batch dialysis is not very feasible because we already seen that batch any batch operation in membrane separation is the worst performer, but they are very important. If you would like to estimate some of the internal parameters, those will be useful to model or calculate the performance of a continuous system. Okay. So, there in case of continuous dialysis, and if the feed and the dialysate flows in the counter current manner, then the driving force will be maximum and you will be getting the best performance. Now, we are talking about the various resistances of offering in the continuous dialysis. We have seen there is a mass transfer boundary layer, or we call it a thin mass transfer film in the feed side as well as in the permeate side. Okay. And in the last class we assumed a partition coefficient simply to connect the surface concentration of the solute at the membrane, and that is in the bulk. Now, in this class we will look into the more realistic type of modeling and the detailed situation what you will encounter in continuous dialysis counter current dialysis operation. Okay. Now, let us first look into various resistances that will be occurring during a continuous dialysis operation. Let us say this is the housing that we will be having, and two compartments will be separated by a dialysis membrane, and this is the feed side and this is the dialysate side, and you are going to send the feed, and the feed is coming out, and on the other hand in the counter current manner you are sending the dialysate and getting the dialysate out dialysate in, this is feed in, feed out. Because of this concentration gradient, the solutes like urea, small molecular solute like urea, creatinine, they will be permeating from the feed side to the dialysate side. So, the feed will be getting devoid of this harmful toxic chemicals. So, that is the idea. So, let us look into the various resistances or the resistive films, those will be occurring. So, this is a schematic of continuous dialyzer, and what are the various resistive films? Let us say this is the feed side, this is the dialysate side, and you will be having a film of solute over the membrane surface in that feed side, a film of the solutes deposited over the dialysate surface. So, we denote this as RF, this is as RD, okay, and there is a resistance offered by membrane itself. So, RF is nothing but the liquid film resistance in feed side, and what is RD? RD is nothing but liquid film resistance at the dialysate site. Okay. So, there are and RDM is the membrane resistance, the resistance offered by the membrane material against the transport of solute through it. So, there are three resistances are in series. One is the liquid film resistance in feed site, another is the membrane resistance, another is the liquid film resistance in the dialysate side. These three resistances are in series, and what is the concentration difference against these three resistances we will be working on. One will be the feed concentration in the bulk CIF, and another is the bulk concentration in the dialysate side, bulk concentration in the feed side and bulk concentration in the dialysate side. Now, let us look into the concentration profile in this scenario. Now, I am just replacing the chambers by the concentrations. So, you will be having, it is just exploded version of the film. Okay. This is the film in feed site, and this is the film in dialysate site. So, the CIF, let us put a bar that indicates the bulk concentration in the feed side, and CIF is the concentration of the solute at the membrane surface in membrane in the feed site. Okay. And there will be the dialysate concentration CID at the membrane surface, and then it goes to the dialysate concentration CID bar. So, let us put the nomenclature. CIF bar is nothing but the bulk concentration of solute in feed side, in feed at steady state, of course. CIF is interface concentration that means solute concentration at interface in feed side, and CID is nothing but the interface concentration in dialysate side, and CID bar is basically the bulk concentration of solute in dialysate side. So, therefore, you will be having 3 resistances, and against these 3 resistances these concentrations will basically operate in the feed side. The concentration that is basically at the 2 ends will be nothing but bulk concentration and the surface concentration. On the membrane surface, the concentration across the membrane is the solute concentration in the feed side and solute concentration at the interface in the dialysate side, and in the dialysate side film the concentration difference is nothing but the surface concentration and the bulk concentration. So, under these 3 resistances you can write down, and there are, since they are occurring in series, you can expect that the flux, that is nothing but the current, will be same in the circuit. Okay, that is coming over, that is going through over this 3 resistances. Now, what is that current? Current in this case will be nothing but the solute flux. What is the definition of the current? It is basically charge flux, right? Charge flux per unit time, that is the current, and in the similar case here it will be the concentration flux, that means per unit area normal to the flow direction per unit time. So, it is a solute flux. So, solute flux you can write down as Ni is nothing but Ci of bar minus Cif divided by the resistance in the film side. We call it in the resistance of the film resistance in the feed side, we call it as Rf. Okay. That is the across liquid film in feed side. Okay. The same will be equal to Dim over L divided by multiplied by Cif minus Cid. So, this is across the dialysis membrane. And this will be nothing but Cid minus Cid bar divided by Rd multiplied by Cid minus Cid bar across liquid film in dialysate site. Okay. So, with this you can define an overall resistance in the circuit. How will you get that? You multiply it by Ni, multiply both side by Rf, okay, multiply both side by this quantity. I have already written it, right. So, this is not required. Okay. Fine. So, just multiply both sides by denominator and add all the equations up. If you really do that, what we will be getting is that Ni multiplied by Rf plus L by Dim plus Rd is equal to Cif bar minus Cif plus CIF minus CID plus CID minus CID bar. I just add all the three equations up. So, all the interface intermediate concentrations will be cancelled out, and you will be getting the difference of two bulk concentration, that is in the feed side and in the dialysate side. So, you can Ni, the solute flux, can be written as now CIF minus CID bar divided by R overall, the RF plus L by DIM plus RD, and these three resistances are in series. So, you can write it as CIF bar minus CID bar divided by R overall. So, we can define an overall resistance. Okay. So, in the process, so the most important thing is to estimate, given a the performance of the concentration to which you would like to reduce the value from the feed concentration, etc. It is very important what is this transmembrane solute flux. To estimate that I discussed in the last class. If you do that, then you can find out that if your target is to remove this much kg per hour, then you can find out what is the membrane area that is required to serve this purpose. So, it will be of extremely helpful in doing the design of dialysis of any dialyzer. Okay. Now, let us go through the more detail how to estimate these resistances, these film resistances in the feed side and the dialysate side, as well as through the membrane. So, overall resistance can be now can be written as R naught is equal to RF plus L by DIM plus RD. Now, if you remember that this overall the film side resistance, this resistance is nothing but inverse of mass transfer coefficient, right. If you remember the definition of the mass transfer coefficient, the solute flux is nothing written as K times concentration difference. So, K is nothing but inverse of resistance, right. So, the overall resistance can be so the resistance, the film resistance is nothing but inverse of mass transfer coefficient, right. So, therefore, you can write down and you cannot determine the values of resistances, what you can estimate the value of mass transfer coefficient from the correlations or relations available to you, like the Sherwood number relations available to you. So, you will be in a position to estimate the mass transfer coefficient, and then you can connect it as a connect into resistances. So, overall resistance can be written as 1 over K overall mass transfer coefficient. Okay. So, this is nothing but 1 over Kf. This Rf is inversely proportional to mass transfer coefficient, Kf is the mass transfer coefficient in the feed side, plus L by Dim plus 1 over Kd. Okay. That means, and how Kf will be estimated? If it is a laminar flow, you can find out you can use the Sherwood number relation K dE over D as 1.86 or 85 Reynolds Smith d by L raised to the power 1 upon 3. Okay. So, you know the Reynolds number in the feed side, you know the properties. So, therefore, you know the Smith number and you know the geometric dimension of the channel you are talking about where the flow is occurring, D equivalent and the length. So, therefore, you can calculate the whole right hand side, you know the equivalent diameter, you know the solute diffusivity, you will be in a position to find out to estimate the mass transfer coefficient. If you put the value of Reynolds number in the feed side, because the generally the dialysate side flow rate will be 2 times or 3 times more compared to the feed side velocity, feed side flow rate. Okay. So, if you put the velocity corresponding to the feed side value, then you will be getting the value of mass transfer coefficient in feed side. If you put the value of dialysate side flow rate, you will be the velocity corresponding to the dialysate side flow rate, you will be and the dimensions in the dialysate channel, then you will be getting the mass transfer coefficient from the dialysate side. If the flow is turbulent, you have to use the Dietz-Boelter relationship to estimate the mass transfer coefficient. Okay. So, depending on your situation, you can estimate the mass transfer coefficients and will be able to calculate the the overall resistance and can find out the overall solute flux that is going into the that is getting transported from the feed side to the dialysate side. Okay. Now, in the next slide, in the next work, what we will be doing, we will be trying to calculate the net mass flux. How to do the calculation? Calculate the net mass flux across the membrane in a dialysate unit. Okay. So, we now will be knowing the operating conditions. Knowing the operating condition means feed flow rate in the dialysis site and in the feed site, the bulk concentrations in the feed site and the dialysate site, and the geometric values like diameter, equivalent diameter, length, etc. So, all these are basically operating conditions and the geometric factors. Knowing this value, we should be able to position to calculate the value of the amount that is of the solute that is being transported across the dialysis membrane. That will serve our purpose. So, let us try to do that. So, let us have a concentration versus area. So, it is a counter current flow. So, therefore, you will be having the CIF and you will be having the outlet COF, okay. And this is CID, this is the inlet for the dialysate and this is the outlet for the dialysate. And we since the way we have done the heat transfer analysis and we derived the delta T LMTD, we will be doing the same analysis here as well. We consider since the height of the channel is constant. So, this is nothing but this area, membrane area is nothing but the same as L, length. So, length multiplied by the total height will give you the total membrane area. Okay. So, we consider a differential element, and in this differential element the dm is the differential amount of mass that will be transported from the feed side to the dialysate side, and here you will be having a concentration difference of delta C, let us say. Okay. So, let us write down what these quantities. What is this dm? Dm is nothing but dm, you can write it dm dot, because per unit time mass flow rate across the differential element dA, and what will be that? It will be nothing but k0 times delta C times dA, delta A, okay, dA. Okay. So, that will be the mass transfer coefficient multiplied by delta C multiplied by the area of mass transfer. So, that will be give you the total mass flow rate in that across the differential element, and we write it as Vf dot is volumetric flow rate of feed. And Vd dot is nothing but the volumetric flow rate of dialysate. Now, these two are basically the operating conditions. You are setting the value of volumetric flow rate in the feed side, you are setting the value of volumetric flow rate on the dialysate side. Okay. So, therefore, the mass balance over the differential element gives you dm dot is equal to minus Vf dot times dCf is equal to Vd dot times dCd. At the steady state, the volumetric flow rate values will be constant. So, since in dm the change in concentration in the feed is delta Cf, okay, in the change in concentration is delta Cd. So, this will be give you the mass balance, and rearrangement of these equations this gives you dCf is nothing but minus dm dot by V f dot, and d C d is nothing but d m dot times V d dot. And what is our delta C? Our delta C is nothing but C f minus C d. And what is d delta C? D delta C is nothing but d C f minus d C d. So, just put the value of d C f here. So, you will be getting an expression of d delta C, and d delta C is nothing but minus 1 over V f dot plus 1 over V d dot times d m dot. Now, we have already seen the expression of d m dot from our previous analysis in terms of mass transfer coefficient, and what is that? If you remember, we just wrote this equation earlier, that d m dot is nothing but k 0 delta C times d a. So, if you put it there, so you will be getting d of delta C is nothing but 1 by bracket 1 over V f dot plus 1 over V d dot times k 0 d a times delta C. Okay. So, this gives almost the same type of analysis in heat transfer, that whatever we have done in a counter current heat transfer analysis. Okay. Now, this equation can now be, you just bring delta C in the denominator on the left hand side, and this equation can be integrated between the inlet and outlet of the flow regime of the equipment. Okay. So, you can integrate the resulting equation across the length of, or length means it is basically proportional to the area, right, length of dialyzer. So, d delta C over delta C from the inlet to the outlet will be nothing but 1 by V f dot plus 1 by V d dot integral k 0 d a from inlet to outlet. From inlet to outlet means over the overall area from 0 to a. At the inlet the area was 0, and the outlet the full area will be available. So, you can get the integration of this. So, you will be getting ln delta C outlet divided by delta C inlet is nothing but minus 1 over V f dot plus 1 over V d dot. Okay. K 0 is constant, it does not depend on the area. So, you will be getting K 0 integration of K 0 d a, okay, from 0 to a. Okay. Now, we can integrate the other equation. What is the other equation? D delta C. D delta C is nothing but 1 over V f dot plus 1 over V d dot times d m dot. Okay. This equation we have derived earlier. We can integrate this out and see what we get between the inlet and the outlet. Okay. And this will be from 0 to m dot, the total mass transfer. So, you will be getting delta C outlet minus delta C inlet is nothing but 1 over V f dot plus 1 over V d dot times m dot. Okay. Now, you can just this integral will be returning you the value k 0 times a, right. It will be giving you a value k 0 times a. Now, divide these two equation, what you will be getting, you can do away with this flow rate as well. Okay. Just divide this equation divided by this equation by this equation, and finally, what you get is that m dot you will be getting as kg per second k 0 times a delta C out minus delta C in divided by ln delta C out divided by delta C in. Okay. So, m dot is nothing but k 0 times a delta C Lm T d. What is Lm T d? It is basically log mean temperature difference. So, what is delta C out? Delta C out is basically change in concentration at the outlet surface. Okay. What is at the outlet surface? What is it? This is C feed out minus C dialysate in, that is delta C out. And what is delta C in? It is C feed in minus C dialysate out. Okay, this is counter current, right. So, that is the definition of delta C out and delta C in. So, the amount of mass that has been transferred from the feed side to the dialysate side per unit time, okay, will be given by this expression K0, that is the overall mass transfer coefficient, area of mass transfer, and delta C LMTD. Delta C LMTD is nothing but some kind of mean concentration existing difference, mean concentration difference existing in the module in terms of feed values both in the the inlet values both in the dialysate and the feed side, and outlet values both in the dialysate and the feed side. So, you will be knowing 4 concentrations, 2 concentration at the inlet, 2 concentration at the outlet. Knowing these values, knowing the operating condition, that means flow rate, etc. By knowing the operating condition means flow rate, right. This using the flow rate you can find out the mass transfer coefficient in the feed side. You will be in a position to calculate the mass transfer coefficient in the dialysate side. If you know the thickness of the membrane and if you know what is the diffusivity of the solute through the membrane DIM, then you can estimate the resistance or the resistance in the porous membrane as well. Now, using these 3 values you will be able to calculate what is the overall mass transfer coefficient. Once you will be able to calculate, and if you have something in your mind, okay, this is my target, that you should get a amount of mass transfer, let us say this much kg per second, let us say 20 milligram per second or something like that, then you will be in a position to calculate what is the membrane area that you are going to set or are going to use to achieve that goal. Now, if this concentration is in kg per meter cube, then the value of m dot will be kg per second. If this concentration is expressed in kilomole per meter cube or moles per liter, then this m dot will be either kilomole per second or mole per second, depending on the concentration of unit of the concentration you are going to have it. Okay. So, we can write it that m dot will be nothing but K0 times A delta C LMTD, and value of K0, the overall mass transfer coefficient will be 1 over Kf plus L over DIM plus 1 over Kd. We know how to estimate the mass transfer coefficient in the feed side, how to estimate the mass transfer coefficient in the dialysate side, and L is the membrane thickness and DIM is the solute diffusivity through membrane. In the last class, we discussed a method how to estimate the solute diffusivity through the membrane phase if we know the bulk diffusivity, but there are also some other factors involved. Those are basically the radius of the solute, equivalent radius of the solute, and the radius of the average radius of the pore. And there are 2 more factors, one was the porosity of the membrane, another was the tortuosity of the membrane. Now, all these quantities are very difficult to estimate, and also in the membrane there will be a pore size distribution, not a single pore. So, using the method that we have discussed in the last class, that will in most of the cases that will give you erroneous results. Okay. So, therefore, what you have to do now in the next, so we know how to estimate Kf, how to estimate Kd. Now, we will see how to estimate the DIM. Estimation of membrane thickness is not a problem at all, that can be easily found out, either in you can use a screw gauge, or if you do not, if it is so fine, you can take a cross section and go to give a scanning electron microscopy image, and you can get the thickness of the membrane. That is absolutely not a problem. So, let us see how we estimate the DIM. Diffusivity in the membrane phase. So, now in this case we should, in order to estimate DIM, we should conduct a batch dialysis operation. What is a batch dialysis that we have discussed in the last class? It is basically batch cell. There are two cells or the 2 chambers are it is separated by a dialysis membrane, and in one chamber, in both the chambers are initially at the same volume, let us say, and you just give some solute concentration in the feed side and let the system and leave the system on its own. So, initially there was no concentration of solute in the dialysate side. So, more solutes will be diffusing through the membrane and coming onto the dialysate side. Now, if you put a start, if you put 2 starters in the feed side and in the dialysate side, the film resistance or the mass transfer coefficient will be almost 0. Okay. So, it will be basically controlled by the diffusion of the of the membrane, diffusion through the membrane. So, therefore, one after some time the concentration in the dialysate will keep on increasing. So, concentration difference will be decreasing. So, there will be after a long time you know when you will be basically you are going to take up samples from the dialysate side and going to measure the concentration. The solute will be diffusing from the feed side to the dialysate side, and it will keep on continuing unless and until the concentration on both the chambers will be equal. Okay. So, that is the idea, and if you write down, so if you can calculate the profile of concentration in the dialysate site, how it varies, then you will be able to estimate the what is DIM. Now, so we will do that. Now, let us look into the schematic situation where whatever we are talking about, we are assuming that there are batch dialysis, it is a batch dialyzer, and some concentration of feed is put there, and it is a dialysate site. Initially, the concentration of the solute in the dialysate site would be equal to 0. Now, both the cells are well stirred. So, therefore, you can assume that film there is nothing called film resistance, that means film resistance does not exist. Stirring is appropriate to remove film resistance. So, therefore, what we will be doing, so by doing that you are assuming that concentrations are uniform both in film side and dialysate side, because you are giving high stirring. So, there is no existence of film, and whatever the concentration here, same concentration will be prevailing anywhere in the chamber. Now, let us write down the governing equation of the solute balance in both the chambers. We do a species balance equation, means solute balance in feed and solute balance in dialysate side. Okay. If you do that and you write down the equation, it is basically accumulation is equal to in minus out. Rate of accumulation is equal to rate of material in minus rate of material out. So, d dt of CID multiplied by the Vd is equal to Am dim times L CIF minus CID. This is the rate of accumulation. Vd is the volume of the liquid in the dialysate site, or you can say if it is fully occupied, then it is the volume of the dialyzer. Okay. And CID is the concentration of the solute in the dialysate site, and the amount of material that is going into the system, it is basically CIF. The total difference is Am times dim L into CIF minus CID. And if you the other side, in the feed side, you will be getting CIF times Vf is equal to minus Am dim L CIF minus CID. Okay. So, this only indicates, this plus sign means the dialysate will be gaining the solute, and the feed side will be, this minus means feed side will be losing the solute. The initial conditions are at t is equal to 0, CIF is equal to CIF naught, that is the initial concentration, and any instantaneous and the concentration CID will be CID naught will be equal to 0 at time t is equal to 0. Okay. Now, these two equations can be solved, they are simultaneous ordinary differential equations. There are several ways one can solve it, and one can really get an analytical solution, but the easier way to solve them, you just use Laplace transform and change the ordinary differential equations into algebraic equations. Then it is basically two algebraic equations, and the two variables can be solved, and then you can take the inverse Laplace and get the equation. Okay. So, apply Laplace transform. Will be the transformed equations are those who have done the mathematics course in the last semester, they are, I think they remember the Laplace transform. Okay. SCID bar is nothing but AM DIM L VD CIF bar minus CID bar. This bar indicates the transformed variables. SC CIF bar minus CIF naught is equal to minus AM DIM over L VF CIF bar minus CID bar. Now, let us assumed AM DIM over L is equal to K, some constant. Okay. So, these above equations becomes SCID bar is equal to K by VD CIF bar minus CID bar, and this becomes SCIF bar minus CIF naught equal to minus K over VF CIF bar minus CID bar. Okay. Now, these two equations, and there are two unknowns 1, 2, and there are two equations. So, they can be easily solved. I am not, again I am omitting couple of steps. So, you can do it by yourself, and you will be getting the overall solution in terms of CID bar, because we are interested in CID, the concentration in the dialyzed site, because we are going to take out samples from the dialyzed site and going to check its concentration. So, we are interested in tracking the concentration profile in the dialyzed site. So, CID bar is nothing but K times VD times CIF naught divided by S square plus SK 1 over VF plus 1 over VD. So, by solving these two equations, you will be getting an expression of concentration, the concentration of solute in the dialyzed site and under the transformed in the transform notation. Okay. Now, we can further simplify it by defining another variable. I am basically getting it in a compact form. A is equal to K times 1 over VF plus 1 over VD. So, CID bar basically becomes K by VD CIF naught divided by A into 1 over S minus 1 over S plus S. So, we make this S square plus SK and all this in rational fractions. Okay. And we know that, and now you are in a position to take the inverse Laplace, because now they are in amenable situation, amenable form. What will be this? This the inverse of this will be 1, and inverse of this will be e to the power minus 80, right. So, take inverse Laplace transform, and you will be getting the variation of solute concentration in the dialysis site as a function of time as CIF naught VF divided by VF plus VD into 1 minus e to the power minus k 1 over VF plus VD times T. And your, so this is the complete solution, and your k is nothing but AM DIM over L. Now, what we can do, you are basically you can make this thing more amenable, because CIF naught is known to you, you know the the initial concentration of the solute in the feed side, the volume of feed chamber, the volume of the dialysis chamber, both are known to you, and you are going to monitor CID as a function of time. So, either you fit a curve in this form, because you know the experimental value. So, you fit a curve and estimate the value of k, or you can just make it more amenable. Let us say this whole thing is b. So, this becomes b into 1 minus e to the power k times, let us say 1 by V f plus 1 over V d is d, okay, d times t. Okay, this let us say b, and this becomes d. Okay. So, now what you can do is just CID over b is nothing but 1 minus e to the power minus k dt. So, e to the power minus k dt is nothing but 1 minus CID times b, and take the log on both sides and see what you get. Okay. Now, we are going to take the log on both sides. It becomes e to the power minus k dt is equal to 1 minus CID times b. So, if you take the log ln 1 minus CID by b is nothing but minus k dt, right. So, now since you are monitoring the value of CID at every point of time, and b is basically the quantity CIF naught into Vf by Vf plus Vd, that is known to you. You plot this quantity versus t. If you plot ln 1 minus CID by b versus t, you are going to expect a straight line with a decreasing slope because of the minus sign. So, you are going to get something like this. Okay. So, these are let us say these are the experimental points. These are the experimental points, you fit a straight line. Now, in this straight line, let us look into the slope. This slope will be nothing but k times d. Okay. And what is d? Capital D? Capital D is basically 1 by Vf plus 1 by Vd. Capital D is nothing but 1 over Vf plus 1 over Vd. So, that will be known to you. So, you can estimate d also. So, therefore, if you can estimate the slope from this straight line and can get the value of k. And what is k? K is nothing but AIM DIM over L is nothing but slope divided by d. So, DIM can be estimated as slope divided by d multiplied by L over AIM, that is the membrane area. This is not AIM, it should be AM. AM is basically the membrane area. I stands for the solute. So, once you will be getting the slope from the fitted straight line, and you know the value of d, there is nothing but the relation between the volume of the feed chamber and the dialysis chamber, and L is the thickness of the membrane. So, you will be able to estimate the value of diffusivity of the solute through the membrane. And the check is, if you know the bulk diffusivity is always known to you through some correlations or from the literature, that will be 2 to 3 order of magnitude less. Compared to bulk values, bulk value of that diffusivity. So, this diffusivity through the membrane, porous membrane, will be around 2 to 3 order of magnitude less compared to the value in the bulk diffusivity. Okay. Now, once you get that, so basically you have to conduct one batch dialysis experiment. That is a very simple experiment, and keep on monitoring the concentration at various time points. Okay. And then from the suitable plot of this quantity, you will be able to calculate or estimate the membrane the diffusivity of the solute in the membrane phase. Now, let us look into the various aspect of design of continuous dialyzer. Let us write down the or draw the schematic once again. Okay. feed is CIF exit dialysate flow rate D exit. So, the F is the feed flow rate and D is the dialysate flow rate at the steady state. CIFI is the concentration of the ith solute in the feed side, feed inlet, and CIFE is nothing but the concentration of ith solute at the feed exit. Similarly, you have CIDI and CEDE. In most of the cases, CIDI will be equal to 0 because we are going to use fresh dialysate to maintain the maximum concentration difference. Okay. So, the assumptions involved in this analysis are first one is constant feed flow rates, feed and dialysate, okay, constant feed and dialysate flow rate. That means, on the steady state they are not varying with time. Dialyzer performance depends on the value of film and membrane resistance. Of course, so you do not have any other driving force or any other thing. So, basically film resistances on both the sides and membrane resistance will dictate the dialyzer performance, and film thickness solely depends on the film thickness solely depends on the geometry and velocity profiles in the channel. So, let us write down the design. So, under these assumptions let us write down the design equations. Okay. So, what are the design equations? The design equations of continuous dialyzer. First one is transmembrane solute flux, that is M I is nothing but K0 overall. This K0 bar is basically overall mass transfer coefficient that we have defined earlier, AM times delta C ith solute LMTD. Okay. Delta C LMTD is nothing but delta C at the inlet minus delta C at the outlet divided by ln delta C at the inlet delta C at the outlet. Okay. Now, molar the flux can also be represented, this can also be represented if you do a overall balance, overall solute balance in the feed side and overall solute balance in the dialysate side. That means, the amount that is going across the dialysis membrane to the dialysate side will be basically the total amount of solute that is coming to that side. So, if you do a the solute flux can also be written as if you do an overall solute balance in the feed side as well as in the dialysate side, you will be getting the same information. So, that means, Mi is nothing but Vf multiplied by CIFI minus CIFE is equal to Vd CIDE minus CIDI. Okay. So, this is the Vf and Vd are constant at the steady state. So, Vf multiplied by CIFI is amount of solute that is going into the feed side, and this multiplied by this means amount of solute that is going out of the feed side. Now, the difference between the two will be nothing but the transmembrane flux, that means the amount of solute that has been transported from the feed side to the dialysate side, and same will be the amount of solute gained in the dialysate side. So, if you know out of these four concentration, or if you know if you do not know one of them, you can get by these balance equations. Okay. Or if you know the concentrations, but you would like to that if you know the all the four concentration, means you are aiming for particular extent of separation. Okay. So, in that case you can design what is the value of Vf by Vd. Okay. So, how much dialysate fluid you will like to keep in your system. Is it 2 times of feed fluid, or is 1.5 times of feed fluid, or is 4 times of feed fluid? That can also be estimated by this. So, some of the parameters may not be known. So, you can estimate them by using this overall balance equation, but these overall balance equations under no way will give the value of membrane area that will be requiring to estimate the to design the dialyzer. That will be coming from this equation. Okay. So, using this equation one can design a continuous dialyzer. Design means how much membrane area is required to effect a particular separation given the other operating conditions, for example, flow rate and concentrations. Now, sometimes one defines the dialyzer efficiency as well. So, this term you should not be you should be familiar with. Dialyzer efficiency, it is defined, and this efficiency is defined as eta, and is defined as actual amount of solute depleted in the feed divided the maximum amount of solute separation possible in a given dialyzer. Okay. What is actual amount of solute that is depleted in the feed? That means volumetric flow rate Vf multiplied by the concentration that is going into the system minus concentration that is going out of the system in the feed side. That is the actual depletion of the solute that you are going to get in the feed side, right. So, this is nothing but the CIFi minus CIFe. So, this difference multiplied with the volumetric flow rate will give you the actual amount that is going to be depleted. What is the maximum amount? Vf CIFi minus Vd times CIDi. In most of the cases, so that is the maximum possible one can have, because this is the amount of solute that is going into the system in the feed side, and this is the amount of solute that is coming into the dialysate side at the entry point. That is the maximum concentration difference one can expect in the whole dialyzer. That is this difference is the maximum concentration difference of the solute one can expect, right, because the maximum solute is occurring at the feed, and this is the maximum solute that is coming into the dialyzer. In most of the cases, CIDi will be equal to 0, because you are going to put fresh dialyzer. Therefore, the fresh dialysate, therefore, the concentration difference is maintained maximum. In most of the cases, CIDi will be equal to 0. So, sometimes by computing this quantity, knowing the values of all the other quantities, one can define the efficiency of the dialyzer as well. In fact, that is the way how to estimate, how to calculate how to design an actual continuous dialyzer. And what is the shortcoming of this model? It is basically a one dimensional model, right. So, we have not considered any any detailed variations of the velocity field. For example, it is we are assuming the velocity, for example, the velocity we are assuming it is the flat profile. The whole velocity is going to be as a plug flow. Because we are calculating the mass transfer coefficient from the cross sectional average velocity. because you know the flow rate. If you put a rotameter, you know the flow rate, you know the cross sectional area, divide the flow rate by the cross sectional area of the flow, you will be getting the average velocity. Based on that average velocity, you are calculating the Reynolds number. Okay. So, it is basically a one dimensional approach that whatever we have done. So, in the next class we will look into a how to model a how to go for a detailed design, but any one dimensional model is good enough to get to design any continuous dialyzer, and in the next class we will look into the higher order models, more accurate models. Okay. Thank you.